When you try to stretch a rubber band, there's a force that tries to pull the rubber band back to its equilibrium, or unstretched length. We call this force that restores a system to its equilibrium a restoring force. For a rubber band, there's only a restoring force in one direction. The rubber band will only try to pull inward to its equilibrium position. However, if you look at an object like a spring, you can see that there would be a restoring force in either direction. If you extend the spring, if you pull it outward, the spring will try to pull back inward to reach its equilibrium length. If you compress the spring and push it inward, it will try to push back outwards, again to get back to its equilibrium or neutral position. What we see from that then is that the force provided by the spring is opposite to the displacement. It's opposite to the displacement from its equilibrium position. And this opposite force means that whatever you try to do to move the spring away from equilibrium, the force is always trying to drag you back to equilibrium. That's a very important point. As long as we don't compress or stretch the spring too much, the force provided by the spring is proportional to the displacement from equilibrium. There's a direct proportionality there. Obviously, if we stretch the spring too much, this proportionality breaks down, and then past a certain point, the spring itself will just break. What we're considering here is smaller compressions or stretchings that are within this region of proportionality. This relationship between the force and displacement of a spring was discovered by Robert Hooke, and he gets credit for it as it's called Hooke's law. Hooke's law says that the force of a spring is proportional to the displacement of that spring. We have a negative sign there as well. Basically, here we're looking at a direct proportionality, a constant of proportionality between the force and how much the spring is stretched. We'll see a little bit more about this constant of proportionality. The negative sign means that the force is in the opposite direction of the displacement of the spring. If we imagine a spring that is attached to a fixed wall, when the spring is by itself and is not being perturbed at all, it will be at its natural length, and so the length of the spring will be at its equilibrium length, some value s. Here, s is our dimension. We don't want to specify whether it's the x or the y direction, so this is some arbitrary direction s, and the spring itself will be at its own equilibrium position. We see that if we extend the spring, if the spring is stretched, then the length of the spring, which is delta s, is the s coordinate of the end of the spring minus the equilibrium value. The equilibrium position is looking at this distance, the distance from equilibrium. When we're stretching the spring, this displacement is positive, and if we're stretching the spring, the force will be negative. The force will try to pull the spring back to its equilibrium position. It wants to be at its equilibrium position. Conversely, if the displacement is negative, meaning the spring is being compressed, meaning that the s coordinate is smaller than the equilibrium coordinate, so you're over to the left of it, that means that you have compressed the spring, and the spring will try and push its way back out, and will give you a positive force. So what we are defining here then is the force that the spring applies and the displacement of the spring. Now there's a common factor of this equilibrium position, and typically what we do is we don't count the equilibrium position, we just count the displacement of the spring from the equilibrium position as our variable in this case. When we look at the equations, you can include the term that has the equilibrium value position, the equilibrium length of the spring there, but basically what happens is every term in every equation has this factor in it, and they all cancel out, and so typically we just leave them out to begin with. What we found, as we mentioned before, looking at this behavior, from this behavior we've derived Hooke's law, which says that the force applied is proportional to the displacement of the spring, and the negative sign tells us the force is opposite to the displacement of the spring, meaning that it is a restoring force. The restoring force is always trying to bring us back to equilibrium, rather than a small displacement causing a greater force, which would cause a greater displacement, etc. That would be an unstable situation. This constant of proportionality that we have, K, is known as the spring constant of the spring. Again, for small displacements of the spring constant is assumed to be a constant fixed amount. Once you can find it for one value of the displacement of the spring, it's assumed to be true for any other value as well. When we think of Hooke's law, we can plot the force as a function of displacement. If we do that, we see that this is following the pattern of y equals mx, where m would be negative k. And so when we look at that on a graph, we would see a linear relationship, a straight line. The slope of this line would be negative k. Hooke's law is one of the reasons why Newton's laws break down, why they become more difficult to deal with. Because when the force depends on position, that means that the acceleration of an object interacting with the spring, the acceleration of that object would depend on position as well. That makes the math very difficult to try and find the position of the object at any point in time when the acceleration itself depends back on the position. You get into differential equations there. We'll touch a little bit on that in later modules. But this is one of the drivers of why we switch over and we consider work and energy rather than acceleration and velocity to understand the motion of particles. Because it's a lot simpler to look at the work done on or by an object that's being acted on by a spring. It's much simpler to look at that than it is to look at the force on that object and thus the acceleration of that object. So we imagine a situation where you have a ball, some sort of object, that is connected to a spring. And the spring is initially compressed, and the object is pushed outward, and it ends up at some stretched position at the end. And if we want to find the work done as the spring goes from its initial compressed position to its stretched position, what we will have to do is we'll say that the work done will be the integral of the force, which depends on our position, integrated ds, integrated over every little piece of motion. So for every little tiny piece of motion, our force is basically constant for that tiny little bit. When we add up all of them with the integral, we get the total amount of work that's done over each tiny little bit of displacement. What you'll notice here as well, in this particular situation, our displacement will be from right to left. That'll be our total displacement. And so what we'll see is that as we displace, as we go from our initial position to the equilibrium, our force is aligned with the displacement, and thus we expect to see positive work in this part of the motion. Later on, as we extend past our spring's equilibrium position, the force changes direction. And in that situation, with the force acting to the left and the displacement continuing to act to the right, here the work becomes negative. And so we'll see what happens when we include both. What we'll do when we want to use Hooke's law, we have an expression for the force. The force being that is provided by the spring, we've said, is negative k times delta s times the displacement, or negative k times s minus s equilibrium, our distance one way or another from the equilibrium position. So that's what we've done here. The negative k is a constant, so it can be pulled out of the integral. The s depends on the ds, and so that's a function that has to stay within the integral. But what we can do is treat this as a w dw substitution, and we'll see that this breaks down and becomes an integral of w dw, which gives us a factor of negative 1/2 k w squared. Our endpoints are the initial position and the final position. So within our function, our initial position, s is less than s equilibrium. And so this would be a negative value times a negative would give you a positive work initially. There'd be a crossover point, and at the end, the final position is greater than the equilibrium position, so you'd have a positive value times a negative would give you negative work overall. Either way, you have dealt with all of that within the integral. You have the integrated form, and you're going to plug in your values. And so we are going to represent the work done as the work done, or the energy at the final position minus the energy at the initial position. You can do, but there's no need to do the energy going from the compressed position to equilibrium and then from equilibrium to the expanded position. You can do that, but that's not necessary. You can do it all in one shot. And basically you're looking at the work done by the spring to get from initial position to a final position, whatever those may be. One example of this spring-like motion is stick-slip motion, which is shown in earthquakes, for example. In this situation, you have tectonic plates that are trying to slide past each other. And so you have a certain amount of elastic energy where the rocks are being stretched apart or they're being pushed on one side, and so they're trying to expand or contract in elastic type motion, but they're held by friction that holds them together. And so what happens is there is some elastic energy in this expansion of even these solid rocks. We'll see that a little bit later as well about the stress and strain on solid objects when you have forces applied to them. So there's a stretchedness of these rocks. There's some internal energy building up from the motion of the tectonic plates, and typically friction holds them together. These rocks don't really want to move relative to each other. But at a certain point, there's so much elastic force that it exceeds the frictional force, and it causes a quick slipping motion where all of this energy stored up in the rock is released. When that happens, you have an earthquake, and that releases that energy. And in fact, what can happen is large pieces of rock can move suddenly a smaller amount or even a quite large amount, where you have a huge amount of friction between these huge tectonic plates, these pieces of rock, but you have a huge amount of friction holding them in place. And when this elastic energy finally exceeds it, there's a huge amount of energy released, and that's why earthquakes can be so destructive.